The chi-squared procedure is named after the Greek letter chi. The chi-squared distribution is the distribution we'll use. It's the Greek letter chi. It's written chi. It's pronounced kai, and it's the ancestor of our x. And if I ever, many years from now, hear you refer to it as the chi distribution, I will hack into Banner and retroactively lower your stats grade. It's also often called the chi-square procedure. And I should actually say at this point that there are a number of procedures called the chi-squared procedure that all depend on the chi-squared distribution. They do many fascinating things. So the procedure we're learning should technically be called the chi-squared procedure for independence. But we'll just call it the chi-squared procedure. It tests whether two categorical variables are associated or independent. We've already tested that, but we've tested it for binary variables. This tests for any two categorical variables, even if they have many possible values. Alternately, you can view it as testing whether the proportions of the different values of one categorical variable differ among two or more populations. So in that sense, it generalizes the two-sample proportion procedure, which does the same thing for binary variables and for exactly two populations. So let's start with an example. This is a group project from a few semesters ago. They were interested in whether what brand of designer clothes you like affects what reality TV show you like, and they chose as your population Fairfield U students. Their explanatory variable was the brand, and their response variable was the TV show. Both of these are categorical but are not binary. They stopped 50 students going into the library on Wednesday evening, and they asked these two questions. Notice, this is a convenience sample. It favored studious students who go to the library on Wednesday evening, and it favored students who are more like the questioners, right? That's the unconscious bias. So if you can connect either of those features to what particular brand such people might prefer, or particular reality TV show, then you've identified a sampling bias. I don't know enough about the brands or the TV shows to be able to do that, but I trust that one can do it. Here's their results. The brands were Louis Vuitton, Ed Hardy, and Abercrombie & Fitch, and the TV shows were Keeping Up with the Kardashians, Jersey Shore, and Teen Mom. You can probably guess when this was by when those shows were popular. And you can see they made a contingency table with the row and column totals. Let me remind you that variables are independent if knowing the value of one gives you no information on the likelihood of the other, and they are associated or related otherwise. And remember, we checked this for categorical variables by looking at conditional proportions, that is, the proportion of each value of the explanatory variable with the given value of the response. So we can compute that here. The percentage of Louis Vuitton wearers who watched Keeping Up with the Kardashians would be the 13 who did both divided by the 27 total of Louis Vuitton, so it would be 48.1%. Similarly, the percentage of Ed Hardy wearers who watched Keeping Up with the Kardashians was 1 divided by 4, and Abercrombie & Fitch is 4 out of 19, or 21.1%. And here's the rest of the table. And remember, we said that if each column of conditional proportions are the same, it's independent. And the idea here is, if, say, that first column, all the conditional proportions were equal, knowing what someone wears tells you nothing about their chances of watching Keeping Up with the Kardashians. So, in this case, since in each column the conditional proportions vary, as long as in any column they vary, we consider the variables associated, not independent. So that means these variables are associated in the sample. But what we're interested in is whether they're associated in the population. That is, in the population as a whole. Are, say, Louis Vuitton wearers more likely to watch Keeping Up with the Kardashians? Notice if, for example, one Ed Hardy wearer switched to liking Keeping Up with the Kardashians, it would then be 50%, which is even higher than Louis Vuitton. So is the difference that we're seeing, even though they're big as conditional proportions, is that are we likely to see a similar difference the next time we took a sample of a similar size? The chi-squared test tells if apparent relationships in data are explainable by random variation. The next time it'll just be different. Or if they probably represent real relationships at the population level. Is it really true that Louis Vuitton wearers are more likely to watch Keeping Up with the Kardashians? And the p-value tells you the chance that you'd see results that look this different if the variables were really independent. If the p-value is small, that is strong evidence that the variables are not independent. I'm going to go back and show you how to use the chi-squared template, and then I'll go through this explanation. But I want to have these numbers here. So the chi-squared template is, of course, on the template page, which I'm at now. It is relating categorical variables, so it's the first column, and we're now dealing with many populations and many samples. So we click on the chi-squared distribution and open it up. Well, it seems to have clicked several times on it. When you open it up, you see it's a little bit more involved procedure. It's got multiple tabs: use, which we've seen before, calc, data, which is in a different place, and then a new tab called expected. The data tab, of course, is where you enter your data, and as usual, it's got dummy rows and columns. It's got a dummy data so that you can see how to enter your data. It's set up to handle 2 rows and 3 columns. If you only have 2 columns, you'll need to delete some. So let's enter our data in. It's a good idea to do the labeling. So I'm going to label this Keeping Up with the Kardashians, Jersey Shore, and Teen Mom. My rows are going to be Louis Vuitton, Ed Hardy, and Abercrombie & Fitch. And I am entering in the data, and there are 3 cautions that I have noticed that I want to warn you about. The first and most important is, notice I did not enter the totals in here. You will often see contingency tables with totals either in the row or the columns or both. If you enter those in, the Excel, in its wisdom, will look at them and think that they're an additional row or column of data. So do not enter the totals, and I'll mention a couple of places where you can check to make sure you didn't make that mistake. That's the most common mistake. If you're ever given, instead of the numbers, if you're ever given the percentages, entering those in will screw the procedure up. It will not work properly. You have to enter in the actual counts, which are integers. And then here's a subtle thing. If you ever are tempted to label your rows and columns by numbers, like 1, 2, 3, Excel will look at that and think that those numbers represent more data. A rare problem, but a devilish one. So I have now entered my data in. From here, you can go straight to the conclusion The conclusion is the p-value. So there is our p-value. But let me talk you through a little bit more of that. On the expected tab, you will see, first of all, it will tell you the number of rows and the number of columns and the total number of observations. Usually you will know that, but if you glance at that, you can confirm that you haven't messed anything up. You've got the right number of rows and columns, so you didn't add a totals row or give it confusing labels. You've got the right number of total observations, so you probably didn't screw up anything you typed in. Then right here, in the middle of the chart, you will see the row and column totals. So even though you didn't enter them in, they're worked out for you here. Down here, we'll come back to this, are what's called the expected results. On the calc page, some things that will show up are the actual p-value is coming from a thing called the chi-squared distribution. The chi-squared distribution has a number of degrees of freedom. They're listed here. And the chi-squared value of your data, that is the statistic whose distribution we're looking at, is 4.08. Okay, let's return. But remember, our p-value is 0.395. So what we did there is we entered the table of counts, not percentages, into the data tab of the chi-squared procedure, remembering not to enter totals, and change the names of your row or column labels if they happen to be numerals, delete excess rows and columns. If you did all that, you're going to get the right p-value. Check the number of rows and columns and the number of observations and the row and column totals given at the top of the expected tab to make sure you've done everything correctly, and then you read off the p-value. There is no choice in null and alternate hypothesis, so there's no need to set anything. And here is the conclusion. We conclude that this data is or is not significant evidence at the alpha significance level that the explanatory variable and response variable are related in the population, or if we're interpreting this as multiple populations and one variable, we would say this is not significant evidence, at the alpha significance level that the proportions of the variable are different among the populations list those populations. So to test at the 5% significance level, that the sample is evidence that there's a relationship between your favorite designer and your favorite reality TV show among Fairfield U students, we enter the data and we read off the p-value of 0.395. This is more than the significance level, so this data is not significant evidence at the 5% level that favorite designer and favorite reality TV show are related in Fairfield U students. Here's what's going on under the hood. Your null hypothesis is that the two variables are independent. That is to say, the conditional proportions are equal in each column. So if you were going to write that as an equation, it would be a bunch of things being equal. So we'll never write the null hypothesis symbolically. The alternate hypothesis is that the variables are associated or related. The way chi-squared does that is it associates to your actual table of data a table of expected data. So this is a table that has the exact same row and column totals as your data does, but the numbers are rearranged so that the variables are independent in your sample, so that the conditional proportions along each column are equal. The expected table is at the bottom of the expected tab, where I showed you. It's what you would expect to get from the sample if the null hypothesis were true. So let's take a look at that. So here's our initial data. We had 13 in Louis Vuitton Keeping Up with the Kardashians. We had 1 in Ed Hardy Keeping Up with the Kardashians, and 4 in Abercrombie and Fish. If we compare that, so that added up to 18, we compare that to the expected column, expected numbers. You see the numbers still add up to 18 if you do the math. But now the percentage of Louis Vuitton wearers who watch Keeping Up with the Kardashians is 9.72 divided by 27. The percentage of Ed Hardy is 1.44 divided by 4. And the percentage of Abercrombie & Fitch is 6.84 divided by 19. Those are all the same percentage. So it's been morphed into a table, same row and column totals, but now the variables are behaving as if they're perfectly independent. So this is what you'd expect to get if the variables were independent, and this is what you actually got. So how far your actual table is from your expected table, if you could measure that as a distance, would be how surprising, would give you a sense of how surprising your result is. And the chi-squared measures that distance. It looks at the differences of each of those cells and combines them in a certain way that one can prove when the variables are independent, one can prove that this chi-squared distribution follows a set distribution that we can compute. So that number that we saw, 4.3, was the chi-squared value. It's computed from those differences between the actual and expected value. You actually square the differences, divide by the expected, and you add them up. The chi-squared distribution, like the t-distribution, depends on a degrees of freedom. And for your edification, the degrees of freedom are calculated by taking the number of rows minus 1 times the number of columns minus 1. But it shows up on the calc page. You get the p-value from this distribution. That degrees of freedom are how many pieces of information do not agree between the expected and the actual data. The row and column totals all agree, so they have some amount of information in common. For what that's worth. Okay, finally, the chi-squared procedure has 3 assumptions. The first 2 should not surprise you. If it's a single sample, then that one sample should be a simple random sample of the one population. If the data was collected by several different samples, then each of them should be a simple random sample of their respective populations, and they should all be independent. The large population assumption, again, not surprising. If it's one sample taken from one homogeneous population, the population has to be at least 20 times the sample size. If several separate samples were taken, each population has to be 20 times at least its respective sample size. The third assumption, remember in categorical variables we had the rule of 15 when it was a single variable and single population. When we got up to 2, it got kind of weaker until the rule of 10 or 5. Now we have many populations and many variables, and it gets weaker still. We're going to, because this is similar to the hypothesis test for comparison of 2 proportions with the two-tailed alternative, because that one was the one that said simply the 2 variables are associated, we're going to use the rule of 5. So we're going to ask that each cell be greater than 5, but now we have many cells. Even that is asking too much. So we're going to only ask, first of all, we're going to look at the expected cells, not the actual, because that has to do with the null hypothesis, which is what we're assuming when we do the calculation. So we're only going to ask that at least 80% of the expected cells have 5 or more in them. That's a kind of a complicated thing to work out. I will show you both how to work it out and what the actual answer is. In our data, here are the expected cells, and you can see that 1, 2, 3, 4 of them, 4 out of 9, do not have 5 or more. So only 5/9 or 50-some% of the expected cells, in this case, have 5 or more, so it fails the rule of 5. Recognize that's a little bit confusing to do, no problem. The use summarizes the assumptions, and it computes what percentage of your expected cells have 5 or more, so you just look at this number, and as long as it's more than 80%, you're good to go. In this case, we fail that assumption. Alright, so let's check our assumptions. Simple random sample. It was a convenient sample, so it's not met. Large population. N was 50, so we need there to be at least 1,000 Fairfield U students. No problem. Rule of 5. We just saw that only 55.6% of expected cells have at least 5, so it is not met. Before I go on, I want to make 2 observations about the chi-squared procedure. One is, we traditionally put the explanatory variable labeling the rows and the response variable labeling the columns in a contingency table, and that is a good habit, but the chi-squared procedure does not care. If you switch the rows and columns, you get the same p-value and the same chi-squared value. It makes no distinction in the procedure between the explanatory and the response variables. So you don't have to worry about that in terms of the calculation. The other is that, as you probably have noticed, this is in some sense the simplest procedure yet, because you have no choice about the null hypothesis and you have no choice about the alternate hypothesis. The only alternate hypothesis is that there is a relationship. This corresponds to the two-tailed alternative on the previous procedures, such as the two-sample proportion. So the way to interpret that is chi-squared does not offer you a way to describe the kind of relationship. If you're relating binary variables, you can say they're positively related or negatively related. That is, gender. When you say gender is associated to following directions, you can conclude that women are more likely to follow directions or less likely. There's a natural sense of a direction. It's much more complicated to describe the nature or direction of the relationship between designer brand and reality TV preference. Even there where we saw it, where we saw a relationship that didn't turn out to be significant, it would be difficult to describe what that relationship is, and we don't. You're welcome to describe it in words once you've concluded there's significant evidence, but the test only addresses whether there's a relationship at all. And the third point I want to make is that you can do the chi-squared procedure when you have 2 binary variables, or when you have 2 populations and 1 binary variable. And the p-value you get out is exactly the p-value that you would get out from the 2-sample proportion using a two-tailed alternative. So they're consistent in that sense. Okay, so here's another example. A couple of years ago, I surveyed my class, as I did in the beginning of the semester, and I asked them their gender and their party affiliation, and I put the data in my website in the file labeled gender_partisan. Let's use this data to test the claim at the 1% level that gender and party affiliation are related. So our null hypothesis is that gender and party affiliation are independent, our alternate is that they're related, and our p-value is 0.878. Let's take a look at that. Gender affects partisanship, sorry. So you can see I have 2 rows, female and male, and 3 columns, Democrat, Independent, Republican. and I am just going to paste that data in here. I have to delete my extra data. That was my cost of my time-saving effort. And this time I'm going to skip straight to the calc template and see that 0.878 is my p-value, which is just what we got here. So I conclude this data is not significant evidence at the 1% level that gender and party affiliation are related in Fairfield U students. And let's check the assumptions. This was a survey of my sections, not a simple random sample of Fairfield U students. Large population, no problem. 68 was the size of my sample if you check the chi-squared page, which means we would need there to be 1,360 students at Fairfield, and the rule of 5 met because 83.3% are 5 or more, as you can see on the Use tab. Okay, after watching, there's a typo for you, this lecture, you should be able to state the null and alternate hypotheses for the chi-squared procedure hypothesis test. There's no confidence interval. There's nothing that measures the strength of the relationship here. You should be able to enter a table of data into the chi-squared procedure template correctly, get the p-value, and state your conclusion in an English sentence. You should be able to use and understand the table of expected values and relate it to the actual data, and you should be able to check the assumptions.